again, Year 12. Hopefully you found the video lesson last time really useful. If you do find these videos useful, please let me know by hitting the like button in YouTube. And if there's anything else that you think that I can include, please let me know either in the comments down on YouTube or of course on Microsoft Teams or even via email. Okay, today we're going to look at part B, which is Châtelier's Principle. And here is a rather fantastic photograph of Le Châtelier. Look at his fantastic glasses and his pretty spectacular moustache. Here's Le Châtelier a bit later on. Right, he was a chemist that was born in the 1850s. He did a bit of a spell in the military, hence his rather splendid uniform over here. But he's widely regarded as one of the fathers of physical chemistry, a really brilliant chemist who worked a lot on, unsurprisingly, on equilibria, which is why this features in Unit 6, Equilibria. And Le Châtelier had this particular principle, he had this thought. The position of equilibrium shifts to try and cancel out any changes that you make. So last video lesson we looked at equilibria in general, and what we're now thinking about is the fact that whilst you've got an equilibrium where you've got the rate of the forward reaction being equal to the rate of the backward reaction in a closed system, if however within that closed system you make some sort of change, be that to temperature, to pressure, to concentration, that the equilibrium will try to oppose that change. It will shift to cancel out any changes that you make to that system. So let's look at some examples so you can see what I mean. Here is an equilibrium between A and B forming C and D. So at equilibrium, the rate at which C and D are formed, this forward arrow here, will be the same as the rate at which A and B are formed from C and D. And Le Châtelier's principle is the position of the equilibrium will shift to try and cancel out any changes that you make. So let's look at this equilibrium. Let's imagine that I allow this equilibrium to establish within a closed system, and then I come along and to that closed system I increase the concentration of A by pumping in more molecules of A. Pause the video in a moment and think about what impact that will have on this equilibrium, given that the position of the equilibrium will shift to try and cancel out, to try and oppose those changes that you've made. What therefore will happen to the position of this equilibrium when you increase the concentration of A? Will that equilibrium go from being slap bang in the middle here to going on to the right, or will it alternatively shift to the left, remembering that it's trying to cancel out or oppose that change? Pause the video, make some notes, and I'll run through the answer in a moment. What will happen is that as you increase the concentration of A, the system shifts the equilibrium to try and cancel out that change. So if you increase the concentration of A, the system opposes that change by pushing the equilibrium to the right to try and decrease the concentration of A. That means that you form more of C and D. So you can see here it says increasing the concentration of A means that more C and D are produced to counteract the change. The equilibrium position moves to the right. Did you get that right? Well done if you did. If you didn't, or need to add to your notes, please pause the video and do so now. Alright, let's look at another example. This time let's look at the effect of temperature, of heat. Remember, Le Châtelier's principle is that the position of the equilibrium shifts to cancel out any changes that you make. Let's deal with that same equilibrium of A reacting with B, forming C and D. However, at the same time, C and D react to form A and B again. I know we don't usually put heat in a chemical equation because heat isn't a chemical, is it? It's energy. I know we don't usually do that, but I'm going to leave this here to help you with this little problem. Bearing in mind the position of equilibrium tries to cancel out any changes. What would happen to this particular equilibrium if the mixture were heated? If we heated the equilibrium, will it shift to the right or will it shift to the left? Pause the video, making some notes, and we'll run through the answer in a moment. What you'd find if you heated up this particular equilibrium, because the forward reaction is exothermic, it gives out heat. That means the reverse reaction is endothermic. You reform your reactants. The forward reaction is exothermic, forming C and D, and heat, giving out heat. The reverse reaction is endothermic. So heating the mixture will mean that the equilibrium will shift in the endothermic direction to try and decrease the amount of heat produced. That counteracts the change. Hopefully that makes sense. Please pause the video now to update your notes if needs be. Right, let's look at another example. Pressure. The position of the equilibrium will shift to cancel out any changes you make. Le Châtelier's principle. Let's say that this time I have a slightly different equilibria. I have A and B, which are both in the gas phase, forming C, which is also in the gas phase. Let's say I compress the mixture. In other words, I increase the pressure. Still a closed system, but I've increased the pressure. What will happen to the position of the equilibrium? Will it shift to the right or will it shift to the left? Remembering, you're attempting to cancel out the changes. That's why the equilibrium will shift. Hopefully you've identified that the equilibrium will shift to the right. The reason being is that on the left here you've got 2 moles of gas, whereas on the right here you've got 1 mole of gas. That means that the pressure is greater on the left-hand side of this equation. So when you increase the pressure, that means the system will oppose that change by decreasing the pressure, forming C. In other words, A and B are going to collide more frequently, and if it shifts the equilibrium to the right-hand side, you form C, where the pressure is lower. The equilibrium is shifted to cancel out the change. Let's look at a particular example of this then. Let's look at one of the favourite reactions of ours that I know that we've covered a great deal at GCSE, the Harbour process. The Harbour process forms ammonia, NH3. And you'll recall that from your GCSE studies that 1 mole of nitrogen, N2, reacts with 3 moles of hydrogen, H2, to form 2 moles of ammonia, of 2 lots of NH3. And this is in equilibrium. In other words, if you have a closed system, a sealed container, where you're reacting nitrogen with hydrogen, you'll form ammonia. Equally, the ammonia can decompose, can break down to reform the nitrogen and the hydrogen. It's a reversible reaction, which if you leave it in a closed system, an equilibrium can become established. Now, the first question people ask me is, well, why should we care? Why should we care about forming ammonia? Well, first of all, ammonia is a hugely important bulk chemical involved in the production of fertilizers. Without ammonia, we couldn't feed the world's population as it stands. However, that's not the reason why Fritz Haber worked so hard to form ammonia. At the start of the First World War, there was an embargo placed on Germany, and the main source of ammonia at the time was bird poo. Ammonia was vitally important in the production of bombs at the time of the First World War. So if you could find a way of producing ammonia which wasn't based on using bird poo, you'd make loads and loads of money. Britain at the time had a series of islands in the Pacific and around South America as part of its colonies that contained huge amounts of bird poo, so we could produce bombs without any difficulty. Germany, however, with this trade embargo, couldn't get hands on our beautiful British bird poo, so they had to use some very, very clever chemistry to form ammonia. Let's look at how this works then. I've got nitrogen, N2, and I react that with 3 molecules, 3 moles of hydrogen gas. The forward reaction is that nitrogen and hydrogen form ammonia, actually 2 lots of ammonia, 2 lots of NH3. And that forward reaction is exothermic. What can also happen though is that those 2 same ammonia molecules can react to make nitrogen and hydrogen again. They can decompose to make N2 and 3 lots of H2. That reverse reaction is endothermic. It takes heat in. The forward reaction is exothermic. It gives heat out. The reverse reaction is endothermic. It takes heat in. And because it's at equilibrium, and because they're both occurring at the same rate, the rate of the forward reaction is the same as the rate of the backward reaction, both reactions are happening at once. It's in equilibrium. So let's look at how this is done industrially. The orange molecules here are hydrogen, the blue molecules here are nitrogen, and the green molecules are ammonia. So you can see that you have a stream of nitrogen and hydrogen molecules coming in here into a gigantic reactor, which is under high pressure, and that's where the chemistry takes place and you form ammonia. Indeed, that's what's borne out by these particular equations. Hydrogen and nitrogen go in, and hydrogen and nitrogen react in this reactor to form ammonia. The temperature and pressure of this particular reaction vessel are very rigorously controlled. And there is also a catalyst in here, an ion catalyst, which isn't shown. As it flows down, it flows into a condenser. And this is much cooler than this reaction vessel up here. As a result, it's cold enough to condense the ammonia, but not cold enough to condense the hydrogen and nitrogen. It's very, very clever. So you can remove liquid ammonia here, and your excess nitrogen and hydrogen are recycled to go back into your reactor. The percentage yield here that you make is the percentage of ammonia in the main reaction vessel here. And we can do several things to try to shift the equilibrium to maximize the yield of ammonia. So let's look at how we can maximize the overall yield of ammonia. What we've learned is the forward reaction is exothermic by some minus 92 kilojoules per mole. How can we therefore shift this equilibrium to the right to make the greatest possible yield of ammonia? Pause the video and think about what you could do to the temperature of the reaction vessel. So we've just stated that the forward reaction is exothermic. Decreasing the temperature would shift the equilibrium to the right, because if you try and increase the temperature, the equilibrium would shift to the right to try and increase the temperature because the forward reaction is exothermic. If we decrease the temperature, the system will try and shift the equilibrium to the right, creating more ammonia, right, shifting it towards the exothermic direction. So here, if you increase the temperature, the equilibrium will shift to the right, favouring the exothermic direction. If you increase the temperature, the endothermic reaction would be favoured towards the left-hand side, plus 92 kilojoules per mole. So hopefully you understood and got that if you decrease the temperature, that will give you the greatest yield of ammonia, because the equilibrium will shift to the right to increase the temperature, I should say. So to get the highest possible yield, you'd want the lowest possible temperature to shift the equilibrium to the right. The problem with that is the rate would be incredibly slow. It would be very, very low. We learned in kinetics that rates of reaction are dependent upon temperature, and if you have a low temperature, you have a low rate of reaction. So to compromise, a temperature of 400 to 450 degrees Celsius, which sounds high but isn't on an industrial scale, it's a kind of a medium temperature, would produce a reasonably high proportion of ammonia, about a yield of about 15%, but in an incredibly short period of time. Hence why the nitrogen and hydrogen are recycled, so that over time you get a higher yield by adopting this particular method. Let's look at the pressure then. What pressure would you want, thinking about the effect of that upon the equilibrium and how the equilibrium will shift, to maximise the ammonia yield? Pause the video, make some notes, and we'll run through something in a minute. Hopefully what you've identified is that you'd want a higher pressure as possible. All of these molecules are gaseous nitrogen, hydrogen and ammonia. If you've got a high pressure, there are 4 molecules on the left hand side here, 1 plus 3, but only 2 molecules on the right. If we increase the pressure, that will shift the equilibrium to the right hand side to counteract the change to decrease the pressure overall. However, 200 atmospheres is used as a compromise rather than something like 500 atmospheres on economic grounds. The higher the pressure, the greater the cost, both of your reaction vessel as it stands, because you're using more material to manufacture it, but also in terms of maintenance. So if you have too high a cost to generate that ammonia, then that will exceed the price you're going to be able to sell the ammonia for. So it's a compromise. Let's look at what we've learned then. We've talked about how we can change 2 conditions inside the reaction vessel for the Harbour process, temperature and pressure. We could use room temperature, somewhere around 20 degrees Celsius, up to 500 degrees C, and for the pressure we could use 1 atmosphere, atmospheric pressure, up to about 500 atmospheres. The problem is, the higher the temperature or the higher the pressure, the more expensive that is. We need to think about what effect that has. The forward reaction is exothermic, that releases heat. So the percentage yield of ammonia is greater at lower temperatures. Remember that if you increase the temperature, the system will oppose that change by decreasing the temperature, shifting the equilibrium to the left in the case of the Harbour process. If you decrease the temperature, the system will oppose that change by trying to make more ammonia, shifting the equilibrium to the right, because that increases the overall temperature. So you'd think that you'd want a low temperature, but as we've learned, low temperatures mean the reaction is slow, so you'd have to wait a long time for your ammonia. So a compromise temperature of about 450 degrees C is used to make the ammonia faster, even though that has a detrimental effect on the yield. It's a compromise. In terms of the pressure, we've talked about how you've got 4 molecules on the left and 2 molecules on the right hand side. If we therefore increase the pressure, the system will try and shift the equilibrium to the right to decrease the pressure, because it's going from 4 molecules to 2 molecules. That will make a larger yield. The issue is that as you increase the pressure, you're going to need thicker pipes. That's expensive, and you're also going to need much larger, thicker reaction vessels to cope with that higher pressure. That has a huge cost implication, so a medium pressure, a compromise pressure of 200 atmospheres is used rather than 500 atmospheres. It's worth mentioning that I don't know what examples they're going to throw at you in an exam in terms of equilibria. They could give you something that you haven't seen before. They could give you the Harbour process. but you need to be able to apply what you know to an unfamiliar situation. Those sorts of questions are what separates the really high grades from the mediocre grades. Please bear that in mind. Next time, we'll look at part C in the unit guide, which is the equilibrium constant Kc, which is according to this expression here. We'll look at this in greater detail. Please make sure that you have some fantastic notes on this. Please also make sure that you are going through and adapting your unit guide, adding to it, ticking off what you can and can't do. What are you going to address on Caboodle? What are you going to look back over your revision guide or textbook on to help you? Are you going to ask me some questions through Microsoft Teams or email me something? I'd also love to know what you think of these video lessons. Are they useful? Do you want me to do something a little bit different? Do you prefer what Dr. Go is doing simply by uploading the PowerPoints for you to take a look at? Let me know either in Microsoft Teams or down here in YouTube in the comments box down below. Thank you ever so much for your attention, Year 12, and I'll see you next time.